So what's going on with those pools in Rio? Why did they turn green, and why did it only happen to the outdoor pools? This seems to be a great Rio-World Chemistry problem for us science geeks who also enjoy the Olympics. We'll quickly discover that it's easy being green when you're playing with pool chemicals. I'm Jim Martin, professor of chemistry at North Carolina State University, and I'm actually researching this very problem. I want to know at the atomic and molecular level what's going on in solutions. We all learn about solubility in general chemistry classes, and copper chloride dissolving in water is a common example. We know that copper chloride, when it dissolves in water, forms the aqueous copper ion and the chloride ions. Now, it's pretty well known that that aqueous copper ion is light blue, while the chloride ions themselves are colorless. But when you go into lab and actually test the theories, well, what we know, we maybe don't completely know. If you have a very dilute solution, it will be nice light blue. But when you have a more concentrated solution, then oftentimes those solutions will be a concentrated green. Clearly something more complex is going on, but if we understand the green, we may understand the pools. When conducting this set of experiments with a group of high school chemistry teachers, while keeping our other eye on the Olympics, we clearly recognized the similarity between the colors that we're getting in these solutions and the colors of the pools in Rio. Now, one of our teachers, who works to maintain the chemical balance at a pool for a summer job, brought in a bunch of chemicals, and I went to the lab and I pulled some chemicals and we got some test kits and we set to exploration. Let's cut right to the chase. You already know the answer as to where green comes from kindergarten. If you scribble with a yellow crayon and a blue crayon, you know you're going to get green. Well, in the chemistry of copper, if the copper ion is only bound to water molecules, it's going to give you a nice blue color. But if copper is only bound to chloride ions, you're going to get yellow color. And in fact, the tetrachlorocuprate anion also forms a yellow color. Now, in a concentrated solution of copper chloride in water, the chloride ions do not fully dissociate from the coppers, resulting in a combination of half hydrated copper ions and half chlorocuprate ions. And so if we take the blue ions and the yellow ions and put them together, we're going to get a green solution. Okay, so how might the blue pool water turn green? There are many chemicals added to a pool to keep it clean from algae, from bacteria, and, well, you know what swimmers add to pools. These chemicals often contain copper. Copper salts are frequently added as an algicide. They also use chlorine. Chlorine is a sterilizing agent that oxidizes things like microorganisms and other pollutants. And there you have it. We're putting all the stuff that we need to be green into our pools. The most simple example for turning copper solutions green using chloride can be seen in this video, where I take a solution of our copper chloride in water, and we're going to add to it a sample of muriatic acid, which is actually hydrochloric acid. This is one of the pool chemicals used to lower the pH, if necessary, to balance the pool water. These two vials have the same concentration of copper chloride in water, 100 times more water than copper chloride. Now, as each drop of muriatic acid hits the surface, you can see yellow colors begin to form. If I keep adding more and more of the muriatic acid, I get more of the yellow until I get the yellow and blue mixing together to give me green. Now, I stopped here at green, but if I would keep adding muriatic acid, eventually the whole solution would turn yellow. Another potential source of chloride comes from materials known as quats. These are quaternary ammonium chloride solutions that are used as algicides in pools. The algicide in the vial here on the right you see is somewhat bluer than the 100:1 copper chloride solution in water that is here on the left. But if I take an equivalent amount of copper that's added to this copper chloride water solution and put it into the surfactant solution, you see it turns a deep shade of emerald green. However, if I dilute this system with pure water, what you'll see is that the algicide and the water don't mix at first. But the blue color starts to return right there at the interface. Now, if I take the system and fully mix it, you will see that once mixed, the blue color of the completely hydrated copper ion returns. Finally, and I think the most likely cause of the green pool water in Rio, is the chlorine source used as a sanitizer. Chlorine acts as a sanitizer by ripping electrons away from microorganisms or other pollutants, oxidizing them in the process of forming chloride ions. The most common source of chlorine used in pools is the hypochlorite anion. When the hypochlorite anion oxidizes stuff, it rips electrons away, creating ions, but in addition to the chloride ion, I form two hydroxide ions. Those hydroxide ions raise the pH of the pool water, requiring the addition of muriatic acid, remember, hydrochloric acid, to bring it back into balance. And adding those chloride ions, remember, turn water green. The hypochlorite does not work well in outdoor pools since it's too easily decomposed by the sunlight. For outdoor pools, it's necessary to use the UV light protected version of chlorine known as trichlorocyanuric acid. I think we found our clue to the Rio culprit, the source of chlorine used only in outdoor pools, the pools where the problem occurred. Trichlorocyanuric acid is not very soluble and thus is the common, slow-release, solid form of chlorine used to sanitize outdoor pools. But importantly, both the product of the oxidation reaction, the cyanurate anion, and the chloride will bind to the copper cations. In alkaline, low chloride environments, the copper cyanurate is purple and can result in a dark ring around the pool walls. But what happens in a chloride-rich environment? In these three vials, I've placed equal amounts of our copper chloride solution, the same 100 water molecules to 1 copper chloride. Now that's a greater concentration than you're going to find in the pools, but I've done that so that we can see the color. In the right two vials, I've also added some of the trichlorocyanuric acid, which you can see as the solid material down at the bottom. Now in this sample on the right, I've added just a little bit of copper wire, which we're using as our model impurity, that stuff that the chlorine is supposed to break down when it is oxidized. Now to speed up this reaction for this demonstration, I heated these reactions to 55 degrees centigrade. That increases the solubility of our materials and speeds up the reaction. When there was nothing in the sample to be oxidized, no pollutants, the water stayed blue. But with our pollutant, in this case the copper model, when we heated it, we oxidized the copper model, forming chloride ions that could react with the copper to form our green color solution, which is almost identical in color to what we see in the pools in Rio. So how do we get the green color to return to our normal blue? Well, what we've got to do is just dilute the system. So I've taken some of our green water, put it into this second vial, and now I'm going to dilute the system with fresh water. You see, as I add the fresh water, our color returns to our normal color of blue. That normal color of blue occurs when the chlorides are so dilute that all we have is the water molecules bound to the copper and no longer is chloride bound to the copper. As for Rio, the initial thought was that the green color was from some mysterious algae bloom, and that resulted in folks adding more chlorine to the system. Oops! As we've just seen, adding more chlorine to the system turns everything green, making the problem worse. What we're going to need to do is dilute the system with fresh water and don't add excess chlorine. So there we have it. Science in the real world. Thanks for watching. I hope you will like and share this video.